Okay, welcome to activity 6, where we're going to be looking at constructing other logic gates from NAND gates. So they're called NAND Gate equivalent circuits. In our previous activity where we looked at designing a comparator, you might remember that the output of the truth table gave us an exclusive NOR truth table. But I wouldn't allow you to design your circuit from just an exclusive NOR. That was too easy. Also, it's not in the GCSE syllabus. And also, it gave us a good opportunity to combine different logic gates to create the same output. And we saw how we could use a NOR gate, an AND gate, and an OR gate to form this exclusive OR output. So in this activity, we're going to look at how these different combinations of NAND gates can produce a different type of logic gate output. So let's build this first one. If we look at this first one, we can see that we have one input. The two inputs to the NAND gate are tied together, where the switch input goes to, and then the output goes to Q. So we're going to be using pins 1, 2, and 3. So I'm going to build that quickly. So I'm going to join 1 and 2 together. I'm going to put A to my input, doesn't matter whether it's pin 1 or 2 seeing as they're joined, and I'm going to connect pin 3 to Q. So we can see here that when switch A is not pressed, Q is a high. When I press A, Q goes low. When I release A, so it's low, Q is a high. So we can see here that A is low, Q is high, A is high, Q is low. That quite clearly is a NOT gate. So it's that type of gate. Let's have a look at our second arrangement. Now we have our two input NAND gate going into this arrangement, which we've already seen here, which is our NOT gate. So we'll label up the pins to avoid any confusion, because it will get a little bit more difficult, especially in the next example. So those are the pins that I'm going to be using. Always refer to your data sheets. So I'm going to, A is going to go to pin 1, B is going to go to pin 2, pin 3 is going to go to pins 5 and 6. So I'm going to join 5 and 6 here. And then connect pin 3 to it. And then my output Q goes to pin 4. So at the moment you can see without either switch being pressed, Q is a low. When I press A, Q is still a low. When I press B, Q is still a low, and when I press A and B, Q goes high. So 0, 0 gives us a 0, 0, 1 gives us a 0, 1, 0 gives us a 0, and then 1, 1 gives us a 1. Now hopefully you'll recognise that as being an AND gate. And perhaps that makes sense, because we've got a NOT gate, which is not, and this is a straightforward NAND gate, so it's not a NAND, therefore it must be an AND gate. Let's look at our last arrangement. So I've got two gates here, which are both NOT gates from the first example, going into this NAND gate here. I'm going to be using pins 1, 2, 3, 6, 5, 4, and now we need a third NAND gate from the 4011, and I'm going to be using 13, 12 and 11. So let's wire that up. It's easier sometimes to start again. So A is going to go to pins 1 and 2, so I'll join 1 and 2. B is going to go to 6 and 5. So I will join 6 and 5. 3 is going to go to 13. Just that one. And 4 is going to go to 12. And then finally, pin 11 is our output. So Q is going to go to pin 11. So, with A and B both 0, Q is low. When I press A, Q goes high. When I press B, Q goes high. And when I press A and B, Q goes high. So that's 0, 0 is a 0, 0, 1 is a 1, 1, 0 is a 1, and 1, 1 is a 1. So you should recognise that as an OR gate. So, what can we conclude from NAND gate equivalence? Well, at the moment we have a NOT gate, an AND gate and an OR gate. This was not a NAND gate, which made it an AND gate. If I were to put this NOT gate onto the end of this AND gate, I would give myself a NAND gate. If I took this NOT gate and put it at the end of the OR gate, so the one input here from the one output here, I would turn it into not an OR gate, so I would turn it into a NOR gate. You can also construct exclusive ORs and exclusive NORs from a more complicated arrangement of different NAND gates. Okay, in activity 7 we are going to design and build a NAND gate equivalent of an EXOR gate. Now, once again, this isn't required for GCSE, but it is required for A-level courses. So, let's look at this whole design process and start with the truth table. So we know that the truth table for an EXOR gate is 0, 1, 1, 0. In other words, when A or B are exclusive, i.e. on their own. So if we look at them from an individual line point of view, let's look at it when Q is a 1. Well, here Q is not a 1, it's a 0. Here Q is a 1, here Q is a 1, and on the last line Q again is a 0. So when is Q a 1 here? Q is a 1 when A is a 1 and B is a 0. In other words, when A and not B. We can say that not B with our bar over, or write it down like that. So in the next line, Q is a 1 when not A and B. So not A, and here I'll write it like this, and B. So what we can do, we can draw our logic diagram out based on those lines there. A and not B. So we have an AND gate. We're going to need an AND gate here. When it's A and not B. Now, I've already drawn the NOT gates in here to help. So when it's A and not B. So here is our A. Here is our not B. Our next line is when it is not A and B. So we need another AND gate. And when it is not A and B. But once again, we have two outputs here, and we need to turn them into one because we only have one output Q. So, how do we say it? Q is a 1 when A and not B, or not A and B. So we can put that into an OR gate. Now the purpose of this is to do NAND gate equivalence. we already know from our previous activity that we can create NOT gates, AND gates and OR gates from these NAND gate arrangements. So, looking at that diagram there, let's draw that out again, but using NAND gates. So, for simplicity's sake, what I'm going to do, I'm just going to draw this all out again. There is my NOT. Here is my A with my NOT A. Okay, so this is NOT A if this is A. This is NOT B if this is B. And this was my AND gate, which was NOT B and A. This was my AND gate. That was NOT A and B. And that all fed into an OR gate, which was the output Q. So our NAND gate equivalent of that circuit is as follows. We have A and we have B. We have two NOT gates, so let's create first of all our NOT B. I'm going to label that for you to make that easier. So there's going to be NOT B. There is going to be NOT A. Now I have an AND gate. And the AND gate arrangement looked like that. So we have a NAND gate which is knotted. And again we have another AND gate which is a NAND gate which is knotted. So these both have two inputs. And then finally I had an OR gate. And my OR gate arrangement is this one here. So I'm going to draw that out. So I have two tied input NAND gates which feed into a NAND gate. Now that's going to be my output Q. So what I have to do here, I have to link all these together. Well, simply the output of the AND gates go to the input of the OR gate. So I'm going to do that first because that's just very easy. Next, the two inputs to these AND gates were, in this case, A and NOT B. So there's my NOT B and there is my A. And this AND gate had NOT A and B. So there is my NOT A and there is my B. Finally, obviously, if this is NOT B, this must be connected to B, and if this is NOT A, this must be connected to A. Now, one of the reasons for doing NAND gate equivalent circuits is because we can reduce the number of ICs that we use, because if you think about it, if I have a NOT gate and I feed it into another NOT gate, so there's one NOT, there's another NOT. If that is a 0 being fed in, the output of this NOT gate will be a 1. So if I'm feeding in that 1 into another NOT gate, the output of it will be a 0. So if I have a 0 going in and I have a 0 coming out, these gates are irrelevant. They are called redundant gates. So we can cross out all redundant gates in a circuit. And if we look here, well, I have a NOT gate, but it doesn't feed into another NOT gate. Here I have a NOT gate, and it feeds directly into this NOT gate. So therefore, I don't need that NOT gate, and I don't need that NOT gate. So I can cross them out. So where I've crossed them out, I'll be able to feed the output of that NAND gate straight into this NAND gate. If you look here, I have the same thing. Another redundant gate. So I've got rid of 4 gates. So what I can now do is I can cross out those and redraw my circuit. So once again, I have A and I have B. I'm now left with this NOT B. I'm left with this NOT A. So I'll just connect those up, not A and not B. I then have this NAND gate, I have this NAND gate, and then I have this NAND gate. I'm trying to draw them in position so that you can see where they all are. So this not B here is going to feed directly into this input here, and then the other input came from A. This not A fed into this input here, and then this other input came from B. We had our two NOT gates on each of these lines, but they are now all gone. So all I need to do is connect where they were from and to, and it looks like that. And immediately you can see we have simplified this circuit no end. If we go back to the beginning, we began with a NOT gate, an AND gate, and an OR gate. We were using 3 separate ICs in that circuit. In its NAND gate equivalent circuit, we were using 1, 2, 3, 4, 5, 6, 7, 8, 9 gates, which would have meant that we used 3 4011 chips. But now we have 1, 2, 3, 4, 5, which means we will need 2 4011 chips, which makes it a lot simpler. And that is the equivalent circuit I would have expected you to get to. But there is actually a slight simplification of that even. If I'd gone back to the original circuit, I could have arrived at this, which is the simplest of the simplifications. And I will just draw it out for you. And this little arrangement here perhaps is a little confusing because you have both inputs going to the same gate, which gets split and then feeds back almost on itself, because you have B going into there, which is a product of B coming into here. If we label up the pins very quickly, making sure you get your right inputs and outputs, we can have a look, as I've already built that circuit here, to check that in fact that acts as an exclusive OR. So our exclusive OR should give us the truth table 0, 1, 1, 0. So when both inputs are low, the output is low. When one of the inputs is high, the output is high. When the other input is high, the output is high. And then when both inputs are high, the output is low. That was how to design an exclusive OR gate from NAND gate equivalents.